Hello everyone and welcome to this video. So in this one we are actually doing Oxford AQA A levels again, not a very usual occurrence, but this was very heavily requested. So we are looking at the most recent paper available for us to solve at this time, which is the Jan25 Unit 2. We did the same for Unit 1 and now we're going on to Unit 2. So let's get started. Just to save time, I've already solved the paper and I'll be going through my thinking process during this solution. Let's start. So question number 1 says, a particle travels at a speed of 3.6 into 10 to the 6 meters per second. De Broglie wavelength is given. You need to find the mass of the particle. So how the De Broglie wavelength is defined is that it's the Planck constant over the momentum, and the momentum is mv. So if I know v, then I can just make mass the subject and find this out. It's just a matter of plugging in values. H, the Planck constant, 6.63 into 10 to the negative 34. Mass is what you need to find. So this is lambda, which is 0.98 pico, 10 to the negative 12, multiplied by its speed. So this mass turns out to be 1.9 into 10 to the negative 28 kg. Next, this says that a cell provides an electric current for 3 hours. So it's a new question now. Figure 1 shows the variation of the current with time. And a current time graph is given. So what you're expected to infer from here is that when you have to find in coulombs the charge transferred in this time of 3 hours, then you'll actually have to calculate the area under this graph. So the area under current time graph is charge. At first sight, it might look like a trapezium, but it's actually not, because this is not ending at 0. This is some length. So I split this into 2. You could have also split this into 2 like this, maybe into a trapezium and a rectangle. I've also done the same, only that my split is different. So I can do area 1, which is going to be this one. So I can see that this is a current of 1 ampere. This is time in hours. So if this is 1.2 hours, I would multiply by 3600 to convert this into seconds. And then that becomes 4320 coulombs. I do the same thing for area 2. Here it's a trapezium. These are our parallel sides. This is the height. So 1.2 till 3, that's 1.8, converting this into hours. And this is 1, and this value is 0.08, because each small box is 0.04. So I get the charge from here as well, adding the both to get the total charge transferred. Let's move on. Question number 3. So this figure shows a experimental arrangement to investigate microwaves. Transmitter produces microwaves of this frequency. I have to find wavelength. Very straightforward. I know that it's part of the EM spec, so it has the speed of light, and I just calculate the wavelength. 3.2. So 3.2 says that a metal grill is placed between the microwave transmitter and the detector as shown in figure 3. As the grill is placed in position, the micrometer reading decreases to 0. So you have a microwave transmitter, the metal grill, the detector, and it's connected to a microammeter. The grill is then rotated in the vertical plane. So initially, when the grill is placed in this position, there's no reading, right? So it decreases to 0. Then it's rotated in the vertical plane by 90 degrees, so it has this orientation now. And the micrometer reading increases to a max. You then rotate it again in that same direction by 90 degrees, and it again decreases to 0. So we can see from the experimental layout that this is basically polarization which is happening, right? So with this orientation, what's happening is that if you have no reading here, so none of the wave is passing through, and here all of the wave is passing through. And for example, if I have to visualize this, I can say that my waves are probably horizontally polarized like this. So that in this case, okay, let me make it even better. You have to like visualize this in a 3D manner. So in this case, when it was horizontal, because these slits are verticals and none of it goes through, but in this position you have a max reading. So state and explain how these observations provide evidence about the nature of microwaves. So I think it's very obvious that polarization is shown. You say that the grill acts as a polarizing filter. In figure 3, the microwaves are completely blocked and none of it gets through, whereas in figure 4, all of it gets through. So it's obvious that it's only something which is attributed to transverse waves. So longitudinal waves cannot be polarized. This means that these are transverse. Next, question number 4. So figure 5 shows how the resistivity of platinum metal wire varies linearly with temperature as shown. So you have a graph of resistivity on the y-axis 10 to the negative 7 meters and temperature in degrees Celsius, and this is a straight line or a linear variation. Length of platinum wire is given at 0 degrees Celsius. Resistance is given. I can read off the resistivity. Diameter is given, so I can find the area and I can then find the length using this relationship, R equals rho L over A. So L equals RA over rho, and then I just rearrange. So the length in this part turns out to be 0.26 meters. 4.2 variation. The linear variation of resistivity with temperature continues up to 200 degrees Celsius. So that is even though the graph is shown up till only 90. Right? So it's going to vary linearly up to 200 as well, is what the examiner says. And you have to find the resistivity when its temperature is at 190 degrees Celsius. So this is a question more on math rather than physics, is that if you figure out how much this changes by, so you can also think about it as the gradient, or if you don't like to work with the graph concepts, what you can also do is you can say that I'm finding how much resistivity changes by for some change in temperature. So I saw that this value was 1.34 here. This is 0.97. So 1.34 minus 0.97 gives me that change in resistivity. And I divide by the temperature, and that basically tells me how much the resistivity changes by when the temperature changes by 1 degree Celsius. So what I've calculated here, this is in units of the resistivity per degree Celsius. I'm not writing out the entire unit to save time here. So now I can see that from we basically use 0 as a reference point, right? So with 0 I saw that the resistivity there is 0.97. So in going from 0 to 190, the temperature changes by 190. So 190 multiplied by this gives me the total change, and then I add it to the initial value of resistivity, which turns out to be 1.75 into 10 to the negative 7. Question number 5. Figure 6 shows a battery connected to a fixed resistor R of resistance 220 ohms and a variable resistor RV. Battery has an EMF of 12 volts, negligible internal resistance. When the resistance of RV is varied between 0 and its max, range of voltmeter readings is 3 volts to 12 volts. Deduce the max resistance of RV. Now I know that when RV is going to be at its max resistance by voltage division, it would have the greatest voltage and it would leave the minimum voltage for R. So I deduce that that must be at the 3 volts reading. So when 3 volts is here, I can also look at the graph and say, I can also look at the diagram and say that 9 volts would be appearing here. But I don't need to do that if I know how to use the voltage divider expression. So that's the resistance of the resistor you want to find the voltage across, divided by the sum of the resistance multiplied by the EMF gives you the voltage. So I would say 220 over 220 plus RV multiplied by 12, that is equal to 3. After this, this is just algebra. I just solve, and RV, the max value of the resistance, turns out to be 660 ohms. The battery develops a significant internal resistance. Explain why a voltmeter reading of 12 volts is now no longer possible. So it makes sense that 12 volts was possible when the resistance of this was set to 0. But when the internal resistance also comes into the mix, so I know that some potential difference would be across the internal resistance. So now the EMF would be shared between the internal resistance and this, right? So because volts would be lost across the internal resistance, you will now have less voltage, lesser than 12, across the load resistance. Figure 7 shows a 0.2 kg mass suspended from a spring. Top of the spring is fixed in place. Mass is displaced vertically downwards and released. Mass spring system oscillates with a frequency of 1.8 Hz. Determine the spring constant. So you'll use this equation where F is given by this 1 over 2 pi root K over M, right? And then from here you just rearrange and find the spring constant. right? So that's what it is, and this basically comes from this equation because I've written it as f, so this might be confusing to some, but t is root m over k. And you also have a 2 pi here. So for f, this would entirely reciprocal, so it becomes 1 over 2 pi root k over m. And that's how I solve this one. Next, figure 8 shows the spring suspended from a vibration generator. Vibration generator is powered by a sig gen. Frequency of the signal generator is slowly increased from 0. Amplitude of oscillation increases and then decreases. And it has a max value at 1.8 hertz. This is basically telling you about resonance, right? So you know that at a certain frequency, when the external frequency, when the driver frequency equals the natural frequency of vibration of the system, you have resonance, and that is what causes the max amplitude. So it's not the same amplitude, it's not that max amplitude that you get either before or after, right? So it said amplitude increases and then decreases after the 1.8 value again. The experiment is repeated with the mass and suspended in a cylinder of water as shown in figure 9. Frequency is again increased from 0, and you have to compare the behavior of this system with what you saw before. Now in the water, it's obviously going to be damped, right, because of the viscous drag here. So I know that the amplitude of oscillation would be less. For all practical purposes, you can say that the resonant frequency is still the same. But in reality, because it decreases slightly, so if somebody also said that it decreases slightly, the examiner also accepts this. Let's go on. Next question, monochromatic light from a laser passes through the center of a narrow single slit. The light forms a pattern on a screen. Describe the appearance, not the formation of the pattern. So it's not talking about why it is formed. So for example, you might be tempted to say that you have constructive interference at the bright fringes at the maxima and destructive interference at the dark spots. But that's not what you have to talk about, you just have to talk about the appearance. So I know that at the center you have a broad central maxima, and then you have your relatively thinner maxima as you keep going on. All of these are equally spaced, and that is equal to x. So their centers are equally spaced like this. So I said that it's a central bright maxima with a second maxima on either side, and you can also say it this way, that they would be less bright than the original one, right? So the intensity also falls off the further you go away from the slits. Width of the slit is decreased and a new pattern is observed on the screen. Describe how this new pattern is different. So I know that if the slit width is decreased, so the fringe width or the fringe spacing goes up. So the bright maxima, they would now be further apart, and then because they're also further apart from the central, their brightness would also decrease. And I totally forgot to write this. I now realized that you would also say that their pattern, their widths are broader. Right, so the central one is the thinnest one, and now they broaden, even as compared to what or how they were before. 7.3, the single slit is replaced with a diffraction grating that has 400 lines per mm. Wavelength of laser light is 530 nm. A diffraction pattern is produced. So this is a question on diffraction gratings. Calculate the max order of the diffraction pattern. So I know the equation is d sine theta equals n lambda. For the max order, I basically work for theta equals 90, right? So if the max is formed at the very edge of the screen, so d sine 90 equals n lambda, I plug in the values. This is 400 lines per mm, so this means 1000 times as many lines per meter. So 400,000 lines per meter, so 1 over that is the spacing for the grating. Divide that by the wavelength, turns out to be 4.76. Even if this was 4.99, I would still round down because I can only see this many at the 90-degree angle. This is what it means. So I can see 4 maxima What if the question said to find the total number of maxima? Then I would use this, that you have 4 on each side and 1 in the center. That would make a total of 9 maxima in this case. Okay, let's go on now. Figure 10 shows 2 small loudspeakers A and B on stands. A and B act as point sources of sound waves. Coherent waves of the same amplitude are emitted from A and B. State what is meant by coherent waves. So coherent waves are waves that have the same frequency and a constant phase difference. Let's go on. A sound meter gives a max reading when placed at the center of line AB. When the meter is moved 5 centimeters towards B along the line AB, the meter reading decreases to a minimum. Explain why the meter gives a minimum reading at this new position. So when you have the max, then probably the waves were in phase, right? Or I can say that in terms of the path difference, there was no path difference. But now the waves must be meeting in such a way that they are 180 degrees or exactly out of phase, or you can say in anti-phase. Similarly, the path difference is also a multiple of the half wavelength now. Odd multiples of the half wavelengths is the condition for destructive interference. So this gives rise to destructive interference. So the resultant amplitude is 0 or is a minimum. Next, as the meter is moved further towards B, another maximum is detected, followed by a regular pattern of max and min. State the distance between two adjacent minima. So you might remember that this is the distance between two nodes. Go on to explain your answer. So I can see here that when it was moved from that point where it was to B, so it was basically a max-min distance. So a max-min distance would be even half of the distance between two max or two min. So because the distance between two max or two min, which is two antinodes or two nodes, is half the wavelength, this distance would be half of that. So this is quarter of the wavelength. So wavelength turns out to be 20 in this case, and then I halve this to find the distance between two minima, and that is also explained here, that the maximum distance is lambda by 4, min distance is lambda by 2. As the meter gets closer to B, the amplitude of minima increases, suggests why. So it makes sense that the further away I go from either of my sources of the waves, the amplitude decreases. So when I get closer to B, the amplitude, or I can say the intensity of the wave from B would be more than the amplitude or intensity from A. So now it does not cancel out as much, and by the principle of superposition, which is that even if it's out of phase, they would now not be completely cancelling. So the resultant amplitude is something, and that is larger than whatever it was before, because now there is not as much cancellation happening as was happening before. Question number 9, very straightforward question about different methods of producing white light. So how is UV light produced in a fluorescent tube? So electrons transfer energy to the atoms by collision. The collision excites the atom to a higher energy level. They then de-excite, emitting a photon, and that corresponds to the gap in energy levels. A LED emits UV photons. White light can be produced from these photons by fluorescence. The LED emits UV radiation at a power of this much. So this is basically the total power of all the photons, and the frequency of a photon is given, so you can find the energy of one of these photons. So I write that formula like this. So ET, the total energy, is the number of photons times the energy of one photon, which I can calculate using HF. And I need N, so I just make that the subject, plug in the values, and find the number of photons. Figure 11 shows part of the characteristic IV graph for the LED. PD across the LED is 3.4 when it emits UV radiation at a power of 42 milliwatts. Determine the efficiency of production of UV radiation. So for 3.4, I can see what this current is, which seems like exactly 19 milliamperes. And this is basically the power that the LED gets. So this is the input power. So I can use P equals to VI to find the input power. And this is the output power. So I can just do output over input to find the efficiency. Next, A different source of white light uses a red, green and blue LED, and the IV characteristic for each of these LEDs is shown. Figure 13 shows the LEDs connected in series to a 27 ohm resistor and a battery of negligible internal resistance. Current in the circuit is 43 milliamperes. Determine the EMF of the battery. The simplest method to do this is to just say that if I have all the voltages, I can just add them to get the EMF. So for this, I can use V equals to IR, so 27 times 43 milliamperes, which turns out to be 1.161. For the others, because I know the current, I can read the graph to find out the voltages across each of these, and then because this is a series circuit, I'll just add all of these up. So that's what I've done here, is that at 43 milliamperes, I've had all of these voltages read. So for example, this is 2.05, this is 2.5, this is 3.05. So these are the voltages which are also given here. I add all of these, and to 2SF, the final answer is 9 volts. Section B now. So this says that figure 14 shows the seed pod of a tree. Pod consists of 2 seeds and 2 wings. When the pod falls, the wings spin to produce an upward force so that the pod travels vertically downwards at a terminal speed. Figure 15 shows how 2 students A and B investigate how one pod falls. Student A marks a horizontal line on the wall at a height of 1.63 meters. The line is at the height of student B's eyes when he stands facing the wall, so parallax error is avoided like this. Student A releases the pod from a point higher than the line. B measures the time for the pod to travel at a terminal speed between the line on the wall and the floor. And we have this height given. Student makes 5 valid measurements of T. Table 1 shows 4 of them in the mean, and you are asked to calculate one of these missing values. So it's very easy that generally I would say this plus this plus this plus this plus this divided by 5 is equal to this. So I'll just have to use some algebra. So first cross multiplying by the 5. So 0.83 times 5 equals this plus this plus this plus this plus this, and I just find out what this is, which turns out to be 0.85. Next, I have to find the percentage uncertainty in the mean value of the time. So I have my max and min values. So now I can subtract them to get the range, and then the half of that would be my uncertainty. So now that I have my absolute uncertainty, I just have to divide it by this, multiply by 100 to express as a percentage. Determine the absolute uncertainty in the mean terminal speed of the pod. Assume that the uncertainty in the height is negligible. So how I would find the speed is by doing distance over time, which is height over time. And if you think about it, if there was a percentage uncertainty in D as well, I would say it's the percentage uncertainty in V plus, so the percentage uncertainty in V is the percentage uncertainty in T plus the percentage uncertainty in D. But there's none of this, right? So first I find the actual value by doing distance over time, 1.63 over my average time, which was 0.83. This turns out to be 1.96. Then they have the same percentage uncertainty, so I just take 11% of this value, which turns out to be 0.22. So the investigation is now repeated with B dropping the pod and A measuring the time. A is taller than B, right? So when we talk about this, A is now going to measure, and A is taller. So previously the level was marked according to B, right? And A is taller, so his eye line would be above the mark, right? So you can say there would be a parallax error, or you can also say this, that because the line will be below student's A's eyes, so he would measure a larger time, and this would lead to a smaller terminal velocity being measured. Question number 11. Figure 16 shows apparatus used to determine the refractive index of a material. Material is placed between 2 internal faces of a glass block. Angle between the 2 internal faces is 90 degrees. Angle between the vertical face and the angled face of the block is 45 degrees. Horizontal ray of monochromatic light traveling in air is incident at 90 degrees to the left face. Refractive index is given of the glass as 1.52. Calculate the change in speed of light as it passes from air to glass. So I know the refractive index of glass, so I can use the formula, which is in terms of the ratios of speed. So refractive index is speed of light divided by speed of light in medium. This is speed of light in air, and this is speed of light in medium. So using this, I calculate the speed of light in the medium, and then I just subtract this and this for the change. The light deviates by 16 degrees from the horizontal as it passes from glass to the material as shown. Calculate the refractive index. So the formula is n1 sine theta 1 equals n2 sine theta 2. Now just to have a look at what my angle of refraction and incidence are really going to be. So because this is 45, this is also 45, and because this is 45, this would also be 45. And that's because this basically makes a 90-degree angle here, right? So if this is 90, this is 45, you can also think about it this way, angles on a straight line, so the sum is 180. So 90, 45, and this thing must be 180, so this turns out to be 45. That's my angle of incidence, which is the angle between the incident ray and the normal. And similarly, if this is 45, so I think this is called vertically opposite angles. So this is also 45. So all of this is my angle of refraction, which is 45 plus 16, which turns out to be 61. So 1.52 sine 45, so the refractive index multiplied by the sine of the angle in that medium equals n2 sine 61, and then I just calculate this as n2, which is 1.23 or 1.2 to 2SF. Next, the apparatus cannot be used to determine refractive indices smaller than a minimum value n min. By considering the critical angle, find the value of n min. Okay, so what would be my n min is, if I think about the critical angle, is when at a certain value, this at a certain value of the refractive index, this just becomes like this. So that this angle, the angle of refraction, becomes 90 degrees, right? So I would say that n1, which is 1.52, sine the critical angle, which would be 45, equals n min, and usually I would write times sine 90, but because it's a critical angle, we know the angle of refraction is 90, so sine 90 is 1. From here I find n min, which turns out to be 1.1, and this is a really good question, which says explain why refractive index smaller than this cannot be used. So this is the minimum value, right? So if my refractive index is smaller than this, then my critical angle would also become smaller, right? You can see it from here, right? So this is basically your constant. If this decreases, then this angle would also decrease. So if the critical angle is less now, so the incidence, the angle of incidence would be more than the critical angle now. So light would basically undergo total internal reflection and not enter the medium at all, right? So it would just go like this, and it would come back like this, and it does not even enter this medium. So how can I calculate the refractive index? So that is what was the idea to be used for this part. Now we are going on to the MCQs, which is section C. So the diagram shows a progressive transverse wave at one instant. Direction of energy transfer is to the right. So if this is the wave at one instant, I've just traced over this and shifted this slightly to the right to find what are the directions of movement after some time. So I can see that to be on this new wave, P must move to the left and P must move down and Q must move up. That's why the answer to this is option B. Next, light of frequency F is incident on a metal surface. Photoelectrons with max kinetic energy are emitted. A graph showing the variation of F with Ek max is plotted. Now the problem is that we are usually used to seeing a graph where you have Ek max on the y and F on the x. But it's not very difficult, because if I rearrange this, I can say that HF equals Ek max plus phi, and then F is Ek max over H plus phi over H, right? So this is right here what's on my y, and Ek max is what's on my x. So I can see from here that the gradient is 1 over the Planck constant. So if it asks for the Planck constant, then that would become 1 over the gradient. What about the y-intercept? So I can say that the y-intercept is phi over h. But if I look at my options, then all of the options are written in terms of the gradient. So I can say 1 over h is just the gradient. So y-intercept is the gradient times phi, and then the phi, the work function value, becomes the y-intercept over the gradient. This is what the examiner calls the f-intercept. So the answer to this one is C. Next. Question number 14, the diagram shows a network of resistors. Equivalent resistor is 120 ohms. I know this is in parallel with this. Plus a 100 equals 120. So if I just subtract by 100 on the other side, that means that the resultant resistance of these two is 20. So 60 inverse plus x inverse equals 20 inverse. You take this to that side, subtract. That is x inverse, which turns out to be 1 over 30. So you inverse that again to get 30. 15. An atom is in its ground state. The ionization energy is obviously the energy required to totally remove the electron from the atom. So that's A. Two coherent sources S and T emit light of wavelength lambda. They are separated by a distance S. Screen lies a distance D connecting S and T. In this arrangement, S is much smaller than D. Distance between the 5th and 7th bright fringes is what? So I know that x equals to lambda d over s. 5th and 7th means it would be twice of this distance, right? Because this is the distance between any two consecutive bright fringes or consecutive dark fringes. So it would be double of that. That's option B. Next, question number 17. A simple pendulum is used to find a value for the acceleration g due to gravity. Period of oscillation is plotted for different lengths L of the pendulum. Graph of t square versus L is a straight line with gradient s. The graph does go through the origin. What is g? So I know of this equation that t equals to 2 pi root L over g. Because I see there's t square plotted here, L plotted here, I must square both sides. So this becomes t square equals to 4 pi square over g times L. So this entire thing is your gradient, which is called s. So if s equals to 4 pi square over g, so g equals 4 pi square over s. 18. Monochromatic light has a wavelength lambda. Each photon has energy E. Which row shows what happens to lambda in E? So when light enters a glass block, it slows down, so its wavelength decreases, but the frequency remains the same. So by the equation E equals to HF, the energy also remains the same. 19. The graph shows the emission spec for an X-ray tube operating at 80 kilovolts. Characteristic lines occur at lambda alpha, lambda beta. Shortest wavelength, which is also called the cutoff or the threshold wavelength, is lambda min. Same X-ray tube is now operated at 40 kilovolts. What happens to lambda alpha, lambda b, and lambda min? So if you remember where lambda min comes from, then it's from this idea that the electric potential energy turns into the energy of the photon, which is HF, or I can write that as HC over lambda min, right? Minimum wavelength corresponds to the max frequency, max energy of the photon, which happens when all of the energy is transformed into the photon energy. So lambda min, you can see from here, is HC over VQ, where V is the accelerating voltage, which is given here. So if you half the voltage, you would double lambda min. But would this change? This would not change because the characteristic lines basically occur due to the transition of electrons between the energy levels. Right? So when the electrons get excited and they also de-excite, emitting a photon corresponding to this wavelength, which is basically coming from the energy difference. So if you're using the same metal, which is usually tungsten, for example, then this would be the same. This location would not change. So lambda alpha unchanged, lambda beta unchanged, but lambda min halves. My bad, lambda min does not halve, it doubles. Okay, let's just scratch this. It's this. 20. A step index optical fiber has a radius A and a cladding of max radius B. Fiber is in air. Which graph shows how the refractive index varies with distance x from the center of the fiber. So as long as I'm within this, it's going to be one refractive index, then it's going to be something else, and then it's going to be 1. Right? So which one ends at 1? That's this and this. Right? So first the value was something, and then it became something else, and then it became 1. But with this, you can see that this is the radius and this is cladding. So because of cladding, the refractive index goes down, not up, and then it becomes 1 in the air. So that's B. A stretched wire vibrates between two fixed points. Frequency of the vibrating wire is this much, tension is T. So you know already what this is talking about. We'll have to use this formula, V equals to root T over mu. Tension is now increased, changes to length and mass per unit length of the wire are negligible. And now the frequency is 600, and you are asked for the new tension in the wire. So if this is V and I need to figure out how F affects T, so instead of V, let me write F lambda. And because I want to see T, so let me actually also square both sides. So I get this equation that T equals to F square lambda square mu. So I can see T is directly proportional to F square. So F, if it becomes 1.5 or 3 over 2 times what it was, then tension would go up by a factor of the square of that. So 3 over 2 square, which becomes 9 over 4. So the tension increases by a factor of 9 over 4. 22. Phase difference between 2 points on a wave is this much. What is the phase difference in degrees? Very, very straightforward. Multiplication by 180 over pi, or if you want to use any sort of unitary method, you can. Here I've basically used this idea that pi corresponds to 180, so what does 0.56 correspond to? And I use the unitary method, which some of you might also know as cross multiplication. 23. So this one, the energy storage of a battery is given in this. So this is basically the charge, if you think about it. It's current times time. So this is the charge, and it says that this battery works at 4.2 volts. So I have to recall this formula, V equals to W over Q. So W equals to VQ. So I multiply these to get the energy as 41 kilojoules to 2SF. Next, two resistors are connected to a cell that has negligible internal resistance. The resistances and currents are shown on the diagram. Which relationship is not correct? So I can come up with a few relationships of my own. Firstly, I can see that I1 would equal I2 plus I3, right? So this is basically that idea that in parallel circuits the current splits up. This is what's entering, so this is what's leaving, and their sums must be the same. So I say I1 equals to I2 plus I3. Next I can say that these two are in parallel. So the current through this branch is I3, the current through this branch is I2. So I can say, because that's equal, so using V equals to IR, so 2I2R equals 3I3R. And then I can do a bit of algebra as well. So I can say that, all right, the R's would cancel out like this. And for example, I can say I2 equals to 3 over 2, or I can say 1.5 I3. I plug this back into this equation to get the different forms. So for example, I know that the answer cannot be this because this is correct. So it cannot be this. And then for the other relationships, I'll plug them with this. So I'm basically simultaneously solving these two equations. So I1 instead of I2, I'll write 1.5 I3. So 1.5 I3 plus I3 becomes 2.5 I3, which is 5 over 2 I3. Cross multiplying, I get 2I1 equals 5 I3. This is also correct, so it cannot be the answer. And then, for example, here I now need the relationship between I1 and I2, right? So I2, if I want I2, so I can say that 2I1 equals 5, and instead of I3, I'll write I2 divided by 1.5, which is 2 over 3 I2, right? So this becomes 2's cancel out. So this becomes 3I1 equals 5I2. This is also correct, so the correct answer, which is the incorrect statement, is going to be option D. Next, 25, the diagram shows the ground state of an electron in two excited states P and Q. Transition of an electron from P to the ground state has a wavelength of this much. Transition of electron from Q to the ground state has a wavelength of this much. And you have to find the energy difference. Now, a mistake that people can make in this one is to use this, that because E equals hc over lambda, some people might say it's delta E equals to hc over delta lambda. This is wrong, right? The easier way is to just find the energy independently and then then just subtract them. So E equals hf, which is hc over lambda, so I do this for both of these, and I just plug in lambda for each of these. So EP turns out to be this, EQ turns out to be this. I subtract, and that turns out to be option A. Now, what is the method which gives you a one-shot answer is this. As some of you might also see, whoever is good at math, that this is basically hc times the change in 1 over lambda. So if you were to do this once, you would have this as hc, and this would be 1 over, for example, here it was 448 nano and 502 nano. So I would do 1 over 448 nano minus 1 over 502 nano, and this would work out. But if I just did the difference of these two in the denominator, this would be wrong. So that sums up this paper. I hope that this helps you out for your exams tomorrow. Best of luck. Go shine your brightest. I have full faith in each and every one of you. So thank you for your time, and like this video, comment if you have any suggestions or if you caught an error. Share this with your friends, and do subscribe to the channel for more cool content like this. See you in the next one.